Today we'll talk about how we can advance our kind of coding practices beyond just writing simple scripts. We will talk about how we create a package, which is a reusable packaging of code that you and others can use. We'll talk about how we test the package, unit tests. Did someone try to join? Oh, okay. How we use a package called Revise to improve the workflow so we don't have to restart Julia as often. How we use the debugger. We'll talk about the next homework, and I will also talk about some patterns and anti-patterns, and how we create a system image so we can speed up the load time of Julia and packages. But first off, there is a style guide in the documentation, and that is a guide. That is not something you have to follow. Most code out there does follow this style guide, so it can be good to be aware of it. And it's things like packages are capitalized, they end with .jl typically. We use upper camel case to distinguish different words. So there is a capital M and a capital P. The same goes for types. They are always upper camel case in Julia. And we typically name packages. So if the package implements a type, the name of the package is typically the type with plural. So this static arrays, it provided type static. So these are just some general guidelines which make it easy to navigate the package ecosystem. Functions in Julia, typically we have lowercase letters. Typically we avoid the underscore, but if it gets too hard to read, we add it there. Right? So get index, you might argue there's supposed to be an underscore there. This is the convention at least to avoid it if it's possible. Argument order. So if your function takes several arguments and they are of different types, we typically have them in this order. Functions come first. So if your function takes another function, we take that first. And the reason is that that enables the special do syntax, which we have talked about before. And that requires the function is first. And then typically the convention is to have things that we mutate. So things that where we change the underlying memory is coming second priority. If we have types, they are high priority, and then we have all other values. And in the end, we have args ... So this is argument slurping. This means that we accept any arbitrary number of arguments, and they have to come last. All of the others, they don't have to come in any particular order, but we typically choose this order. This is particularly important if we want to make use of the do syntax. Another convention is that if we modify an input argument inside the function, we warn the user or the caller of the function that we are mutating A by adding the exclamation mark here in the name. That is not something the compiler cares about. It's just a convention in the naming, but it's useful and most people do it. So here are some examples. Sum. We have the function. So we could write sum A dims do, and then calculate the adds. We have keyword arguments always come last. Here we have a function rand with an exclamation mark, and the reason is that it mutates A. So it uses already pre-allocated memory A and fills that with random numbers. And then comes the type. It says we want to fill the memory with this type. Here is another convention. We say foo x, it accepts a real. So a lot of people, they write float 64 here. But there is typically no reason to restrict yourself that heavily. If the function would work equally well for any real number, try to be as loose as possible in the type restrictions here. And there is a long list of additional style guide in the documentation. It can be nice to read through it. If you deviate from this, that's perfectly fine, and you're allowed to do that. If you send it to a Julia programmer who's used to the people following the style guide, it makes the code hard to navigate. So it might be nice to follow it.
I have a question.
Yep.
The avoid and used, are they equivalent?
Yeah, they are equivalent in this case, but this is much more verbose than this one in this particular case. We only introduce type parameters if we need them for some particular reason.
There's no default one.
No, not in this case. Packages in Julia they have a particular structure. You can generate that structure automatically in the package manager by typing generate my test package. But I would actually recommend you to use a package called pkg templates.jl. I will link that in the slides when I upload them later. What that does is you enter your information, name, email, some configuration options, and that package generates not only this package structure, but also adds a license file, adds GitHub Actions, and all of these things. And I will talk about what GitHub Actions is. But on the top level, we have a folder that has the same name as the package without the .jl typically. Inside, we have a folder called source, and we typically have a folder called test calls. Inside source, there is a file with the same name as the package ending in .jl, and that is the main entry point on your package. So when you call using my test package, the code inside my test package will be run. If you call generate my test package, this will be created for you. But if you call generate with the PKG templates, you will get a lot of additional stuff that is usually wanted. There is also a project.toml. This is kind of a manifest file. Here you specify all the dependencies of your project. And if you have compatibility bounds on your dependencies, those are listed there. You don't need to modify very much in this by hand. You can use the package manager to do that, and we will see how we do that. It's generally good to add compat bounds on your package, saying that I require this package, and I support versions up to and including this version, but no higher. And the reason is that in Julia, we follow semantic versioning. So if you use package version 1 of a particular dependence, if that package releases version 2, the only reason to do that is because they have introduced breaking changes, which means that previously existing code is unlikely to work with a new version. So you cannot assume by default that you are compatible with all versions, future versions of this package. So if you say, I use my other package or someone else's package, and I use version 1, Julia will not automatically update anything to version 2 because that's assumed to not be compatible. That's good to keep in mind.
To be clear, when this other person generates something 1.1.
1.1 is fine. That indicates maybe a new feature. But if the other person releases version 2, that indicates that the code is broken.
So when you said that you should write, I support up to this and this version, what was it?
Yeah, I can show you an example.
Yeah.
So here is the project file for control systems. The name of the package is control systems. It has a UUID. The authors is this department, and so on. And here are the dependencies. So we see it depends on control system base, delay, diff, EQ, and so on. Here's the compatibility bounds. It says that the control systems base, we are compatible with version 1. And that automatically means everything up to, but not including version 2.
Oh, okay.
And here we say that we require at least 5.31 of delay DFEQ. So 5.32 is perfectly fine, but 5.30 is not.
Okay.
Because there was probably a fix introduced here that we require.
Is 5.4 acceptable for delay defect?
Yeah, everything below 6.
Okay.
6 indicates a breaking change.
So line 29, what does that mean?
That means we are compatible with version 5.2 and above, up to below 6, but also version 6. So
why not 6.1?
6.1 automatically, because that's not a breaking change. So if these rules are confusing, they are called semantic versioning. You can find probably lots of guides online on how that works. Yep.
Does control system then have some automated testing of all combinations of all versions?
No, that's not. it relies on all of these packages also following semantic versioning. So what you can do is you can do you run your own test suite, and then you run some downstream test suites, but then you can't guarantee that you're compatible with every combination. But if they have followed semantic versioning successfully, you will be compatible. Then by mistake, they might have introduced a breaking change and not indicated it in their version number. And we can't guard against that. What you can do is that next to this file, there will also be a file generated that is called manifest.tom. And that specifies each package that was used and the exact version. So if you want exact reproducibility, you can include also this manifest, but that's typically not needed. But that gives you exact versions, not only any version within components. All right. Yeah, and then these slides were generated. Yeah.
When the major version is 0.
Yeah.
That's a special.
When the major version is 0, that typically indicates that the package is not get ready for production. And then Julia has a special version of semantic versioning, and then also so if we say x.y.z. Yeah. Then a change here indicates a breaking change. But these are details, and I didn't intend to go that detailed into that, but you can read in the package manager documentation for the exact rules here. So, but if that's 0, it typically means that the package author hasn't considered it ready for release.
And the version, is that specified in your project.toml that you showed in the first few lines of control system?
Yep. So this is the current version of control systems on the
So
master
when you
version.
want to bump the version, you just increment that and push to your repository.
Yeah. So then I change. If I make a patch release, I increment the 0. If I make add a new feature, I increment the 5 there. Yep. Let's see. Now we will look at the simple package. This is in the Julia control organization, discrete PIDs. Here we have the typical folder structure. We have source, we have test, there is a git ignore, I don't know why that is there actually. There is an open source license. That's generated automatically if you choose the license in PKG templates. There is a project file and a README, and the README is marked down so GitHub can display it. If your package is very small, it might be enough to have the README as documentation. If you have a large, extensive package, maybe you want dedicated documentation that is built automatically. Then there is this folder .github/workflows. We can look what's inside of there. This is part of GitHub's integrated continuous integration, CI. And continuous integration is just a fancy word for stuff that happens automatically when you make a change or when something you want to respond to happens. So here is a file, there are 3 files. There is one called tagbot, and that's a bot that's when I make a new release, then this bot will create a tag on my GitHub repository, okay? There is something called compat helper. That's another bot that checks every once per day. It checks, does any of my dependency, do they have a new version? And if they do, it submits a pull request to the repository and adds compatibility for that version. And runs the, make sure the test runs, and if you're compatible with that, you can bump the compat. But the most interesting one is ci.yml for continuous integration. So this is an YML file. I don't expect you to understand what it does here. How you typically set this up is you copy that from another repository. But what it does is when we push to the branch main, we run a bunch of things, and in the end here, we can select which operating system we run it on, which Julia version we run it on. And then what it does, it calls Julia action setup Julia, and then Julia action build package and run test. So what this does is it runs all the tests I have written and make sure that they pass. And if they do not pass, you get the red flag saying that, yeah, whatever you just did didn't work or broke something. And if you get the green checkbox and your tests are well written, that's a good indication that the change you just made to the code is acceptable and it will not break the functionality you have written there. So this will be part of the homework to set up this kind of workflow. You can do it on GitHub with GitHub Actions, but you can also do it on GitLab. Then the file will look slightly different, but there is templates out there. You can just copy paste essentially. So we will see how it looks here in GitHub. Let's see a pull request. There is one closed pull request in this little repository. Someone added a feed forward term to the controller. And what happened then is that there are a few commits, and then in the bottom here somewhere, can I see the details? I can't see here maybe. Why can't I see? Anyway, this check mark here is an indicating that he broke the test somehow. So I probably had a comment saying that, yeah, this broke something, so you need to fix that. And then in the end, it was fixed. I don't know why I can't see the full status report here. But the result in the README, typically we show something like this, continuous integration passing. And if you happen to merge a commit that breaks the functionality, you get a red flag here. And then there is a code coverage. We test 98% of the code. So that's an indication that we ran the code. It's not an indication that we did very well thought through tests or anything. But if this is 0, it means that you didn't have any tests at least. So if we look inside the test folder, there is always a file called run tests. That's the main entry point that will be run when you test the package. And inside here, you can write tests, but you can also include other test files and so on. So typically inside such a test file, we use the package we're testing. We use the test package. This is standard library. We might use some other packages that are required for testing purposes. Then here I have something called a test set. It's named. It's just to group tests together when you get a report in the end. And then I write code to perform tests. So what this does here is, yeah, it creates a controller and it simulates it. And here it says test this result.y is approximately equal to the other result.y. So hopefully I have written a well thought through test, and these two are supposed to be equal. And if they are not, you will get an angry red message from this test macro. So we can see how it looks when we run that. We have Julia here. Yeah. So what did I do here now? I went into the package manager. I called status for no reason. And then I activated the folder, local folder of this package, because I have it checked out for development. So now it says here discrete PIDs, and then I wrote test. So now the test for that package will be run. We see it does some pre-compilation of packages. It lists here exactly the versions of all packages it has loaded. And then it does some pre-compilation there. So we can leave that for a while and come back to it and see if it has run the tests. But that's essentially the workflow for testing. You write the tests, you can run them manually inside VS Code, or you can call test. But crucially, when you push to your repository on GitHub or GitLab, whatever you choose, you can set up so there is a bot that also runs the test. And that's very good because maybe locally you have checked out some package on master branch, and maybe you have some change you forgot to push, and if you don't push that change, the test will not pass. And also, if someone else submits a pull request to your package, you want to be confident that if you merge that code, you will not break your own code. And if you have written good tests and the tests pass on the pull request from this kind stranger, you are confident that that's a good implementation and it will not break anything. But it, of course, relies on you having written nice tests, and that's definitely not trivial. But when we implement something, we always test it for ourselves, right? If I write a body plot, I try with a system where I know how the body plot is supposed to look, and does it produce what I expect? Okay, so body plots are difficult to test, but you can test the body function itself, that the frequency response magnitude is correct. Okay, so we always do these kind of tests, but I would like to encourage you to actually put those small tests in the test folder under a run test and have them run automatically when you push changes to your repository. In fact, the homework requires you to do so. The homework would be that you create a package and you write some tests and you make sure that continuous integration runs the test. Let's see here. Where were we? Yes. Yeah, so when we add tests, there will be an additional folder with a file called run test there. But if you use these PKG templates, that would be set up automatically for you. Yeah, and then I mentioned it's good to have a license. If you want it to be open source license, include a license. If you have no license, the default is extremely restrictive. GitHub has a minimum default license if you publish it to GitHub, but if you want other people to use it, you can use an open source license. Most Julia itself and most Julia packages have the MIT license. It means that anyone is free to do whatever they want with it, as long as they give you recognition if they publish it. A README is nice to have that describes what your package does, and maybe links to either the README contains the documentation or links to a more extended documentation. And then, yeah, you can have a git ignore if there are a bunch of files and folders you don't want to include. So the slides here suggest to set up continuous integration with Travis. That is old advice. The newest advice, if you use GitHub, is to use GitHub Actions. Travis is no longer working properly. GitHub Actions is what I showed you, the GitHub workflows file. And there are guides online I can link to for how to do that. All right, package location. So most Julia packages are hosted on GitHub. That is not a requirement. You can host them anywhere. The package manager understands Git, so it's definitely by far the most smooth experience if you use Git. You could, I don't know if you can actually use SVN or something else, but I suggest using Git. If you have a package that you want everyone in the whole world to be able to install conveniently using the package manager, you can register that in the general repository, general registry. And then you can install it by just typing add and the name of the package. If you don't do that, you can still add the package, but then you need to type add and the full URL to the package. Yeah, if you want to contribute to any package out in the ecosystem, they're almost all hosted on GitHub, so you can submit pull requests and open issues and stuff like that, just like on any other GitHub Git repository. So that's quite smooth. Yeah, if you want to modify an existing package, say that you want to modify the control system package, it's definitely easiest if you have a GitHub account, since that package is hosted on GitHub. If you create your own package, you can create a repository on GitHub, and if you want it to be a Julia package, we typically make them end with .jl. That's a convention. It's not a requirement. Then you git clone that, so you get the files on your local machine. You can also do that using the package manager by saying develop and the URL to the package. The package manager will do the git clone for you. Compared to Julia. And very often the different idioms in Julia are due to performance. So I will try to list some of them that I see quite often that you maybe can recognize yourself. So we'll talk about also how we can use multiple dispatch instead of what I call manual dispatch, which is quite common in other languages. In particular, we will see how we can use multiple dispatch to our advantage when it comes to code reuse. So writing a small amount of code that can do a large amount of tasks. So here's the first anti-pattern. And here is some Python code. It implements a class called shape. So that's some kind of geometrical shape. And then there are two kind of concrete classes that inherits from shape. It's a rectangle and ellipse. So if we want to intersect the two shapes with each other, we might write something that looks like this. So either we could write intersect could be a method of this, but then you have the problem that when you intersect a rectangle and an ellipse, should the rectangle have to know about all different shapes and then so rectangle knows how to intersect with an ellipse, but the ellipse have to know how to intersect with a rectangle. There is some kind of a weird symmetry there, and we have to implement twice. So instead, we might do something like this: that we have a function. It takes two shapes. If the first one is a rectangle and the second one is an ellipse, then we do something, right? And otherwise, if it's a rectangle and a rectangle, then we do something else. Okay, and why is this not good? And one reason is that if we want to implement a new shape now, and we want to be able to intersect that with other shapes, then we must even modify this intersect function written here. So if this belongs in a package and you want to add someone else's package and you want to add a new shape, then you actually must modify that intersect method that belongs to someone else. So that's not very nice. How would we do it in Julia? We would have an abstract type, abstract shape, and the two concrete shapes are both subtypes of that. And then we have three different methods here. And here we intersect a rectangle and an ellipse. And yeah, the implementation, I don't show it. But there is a separate implementation here that intersects two rectangles. And the nice thing here is that if you come in your own code and you introduce now a circle, you can easily add such a method in your code that implements how to intersect with a rectangle and a circle. So you don't need to modify any existing code. And that's one of the main benefits of making use of this. Another common problem is that we dispatch on strings. So here is the function. It processes some data, and it has an option here for how to pre-process. And that's a string. And if pre-process, if we have passed in sum to 1, then we make sure that the data sums to 1. It divides by the sum. But if we say norm 1, it does the same, but it makes sure it divides by the norm. And if we say filter, then yeah, we filter the data. So why is this bad? Once again, if you want to add a custom preprocessor, you have to go in and modify this code. You cannot add functionality outside of this function. So how could we do it instead? One way is that we just accept a string function here instead. So this is now a function. It can be any function. We can provide some default ones if we want to make it nice for the user. But then we just say here it's actually trigger. We could have done this outside. But here we just call that function, and it doesn't matter what it does. It produces some data, and then we do something. But now this is extendable. The user can pass in any function, and it will still work, right? So that's definitely more flexible. But we can also do it with types. So this looks a bit more verbose, but there might be a reason we want to do this. So here we have an abstract type, abstract preprocessor, and then we have a bunch of concrete preprocessor. One is called sum_to_1, and there is a function that takes the preprocessor method and then the data, and it implements the processing. So then, where do I have the actual? I don't call it. But then you would, inside the function we had here, do something. You would pass along the preprocessor, and that would make sure that we dispatch to the correct preprocessor. So we would call, for instance, preprocessor, and data. All right, and it would dispatch to one of these implementations depending on which preprocessor we have passed in. So this is much more verbose than the function approach. So why would we like to use this approach? If we would like to specialize more than one behavior based on the processor type. So maybe there is a pre-process and a post-process. All right. If you do the function approach, you need to pass in both the pre-processing function and the post-processing function. But if you use this approach, you can implement two methods, pre-process, post-process, and then you just pass in one kind of struct that determines the behavior. And this, of course, extends to arbitrary number of behaviors. So if you find yourself in that situation, using types is more beneficial. But for this particular example, I would say that the function approach is by far the most clear and concise. And it's extremely easy to extend for the user.
What was this in the end on the last slide with the cutoff?
Yeah, so the filter here has some optional parameters. It has a cutoff frequency. So it's just to show that you can put in a function, you can close over this value. So you can have an anonymous function that filters with a particular cutoff frequency. But if you create a structure, you could put that inside as an option. And then when you call pre-process, it filters with a F cutoff.
When calling the first two pre-process implementations, are those called with a type or with some instance of the type?
Yeah, nice question. I have omitted a name for the argument. But I require whatever argument it is, it must be of this type. And that's because here I only use the structure for dispatch purposes. I don't actually use the value that was passed in. However, here I do, because the value here has this cutoff stored inside it. So I can omit the name of an argument if I just want to make use of the fact that it's of a particular type. But here I needed the value also because I
But when calling pre-process in my code, would I have to provide a value?
an instance of it, yeah. You could also dispatch based on a type only, but it's strictly more powerful to dispatch on a value of a particular type, because you can at any point decide you want to add type fields here.
So just create the value with the default constructor of sum_to_1.
Exactly, sum_to_1 parentheses, then you have a value of that type. All right. Here's another anti-pattern, and we have several names for the same function, I say. And here we say optimize gradient descent. It takes a problem and some data, and it loops, and it takes a gradient descent step. Then it checks convergence, check the gradient, check function evaluations, yeah. And then we have another function. It also optimizes, but with a different optimizer, right? BFGS instead. So what's the drawback here? So there are tons of drawbacks in this case. We have copy-pasted code, so this is obviously not good. We have the same code here as we do here. The only difference is that we do take the step in different ways. The gradient descent and the BFGS steps, they are different. So in Julia language, this is the same function. This function is optimizing the optimization problem. But the method of doing it is different. And the only place the method is different is in the step function. So in Julia with types and dispatch, we might do it like this instead. We have an abstract optimizer. We have a concrete one, gradient descent, that's the step size. We have another concrete one, BFGS. We might have Newton and so on. And then we have 3 different step implementations. So if we step with this optimizer, X and problem, then we implement it like this. And if we step with the BFGS, then we have a different implementation, right? But now it's a bit unfortunate we can't really see the slide all the way down. See if I can. Yeah, then we can implement a single function that loops, and it just calls step with the algorithm we have chosen as the first parameter. And depending on the type of the algorithm, we will dispatch to the correct step here. And then the rest is the same. So in single dispatch languages like Python, you could also do this because we only dispatch based on the algorithm. We don't dispatch based on X and the problem type. We could do that also if we had a reason to do so. But this is definitely more generic. You use the same implementation here for all 3 algorithms. I would say this is to prefer. All right, let's see. I don't understand why it's giving me a problem. But here it's just a list of other anti-patterns that I see quite commonly used in Julia. So here we have spoken about this last week. Repeat matrix. Repeat the same memory many times. There is almost never a reason to do that because you only have a certain amount of information, the information contained in V. If you repeat that several times, you're just using unnecessary memory. And you do that to broadcast the multiplication with A to match the size of A. In Julia, you don't have to do that. This is done implicitly. If the sizes don't match, it will broadcast one dimension as appropriate. I see a lot of people collect ranges. So this is a special kind of type. It's called a unit range. It stores just number 1 and number 100, and it doesn't need to store all the elements in between. If you call collect, you get an actual vector in memory with all the elements in. And if all you're going to do is the loop over it, you don't need to instantiate that memory. It's inefficient and expensive. So instead, we just write like this. And this thing behaves just like any other vector, except if you try to modify one of the elements, this is immutable. So if you want to edit the contents of the vector, you need to collect it. Otherwise, you should avoid it. In Julia, matrices and vectors are different things. They are all arrays, but they have different number of dimensions. So if you call rand 10,1, that is a matrix. And if you intended to have a vector, you should just not write comma 1. They are different types. And they behave differently in linear algebra operations and stuff like that. I have written just 0. It's very often the case that we don't want to write a literal 0 in the code. And the reason is that this has a type. On my machine, it has type int64. And that might sometimes be what I want, but not always. And if I want the code to be generic with respect to the types the user uses, I should use the function 0. I can call 0 of an element. I get the multiplicative identity for that element. I can, if I want to have a 0 of the same type as whatever is in the vector, I call 0 of the element type of a particular vector. And that gives you a generic 0 that has the correct type for no matter what the user passes in. If we want to allocate some memory and we want to use that memory to write into, a common way of doing that is to write vector, and the element type is type of something undefined. So this just allocate the memory, I don't care what's in there, and of a particular name. And this is bad because you have hard-coded the type of the vector. Very often you can make use of the function similar if you have another vector. So say that you want a vector that is similar to x. If you just say similar x, it's the same element type, same vector type, and the same sizes. But you can change the size, you can change the element type, and so on with additional arguments here. And the reason this is to be preferred is that if x is a GPU array that computes on the GPU, then you have hard-coded CPU array here. But if you do similar, you get a GPU array instead. So this is more generic. And also you need to figure out what type, stuff like that here. Actually, I should have written L type. This is incorrect, not type. It should be L type. This is very common, mean of the squared values of x. Why is this bad? Because we allocate the vector here. The correct way of doing this is mean and a function, abs2. That's just for real values, it doesn't matter. For complex values, it takes the absolute value first. So it applies this function before taking the mean. They compute the same thing, but this one does it without allocation. This one allocates a copy of x. The next one is here I have hard-coded that to say I only accept the type float 64. And then I just do the square. Okay, so that's stupid. I can do that with the ints. I can do it with the float 32. I can do it with matrices. So I should probably just not say anything here. I should just write like that. If I want to change the behavior of f depending on the type, then yes, I should have some type annotation to make dispatch work. But if I only have a single implementation of f, at the very least, I should say real. It works for any real value, but actually it works for any number and a matrix also. So try not to restrict yourself more than necessary because it just limits how generic your code is. So if I now would like to use automatic differentiation on this function, that will not work if I use a forward mode AD, because that uses a special type called a dual number. So now by writing this, you have essentially blocked automatic differentiation from working here. But this is perfectly valid. There's no performance loss in writing like this. This is perfectly valid implementation of it. Here I said middle of x, which is a vector. It takes the middle element. Here's a nice thing. You can do arithmetic with the end keyword. So you can take stuff like a max, minimum of end and some value and stuff like that. And here I take n divided by 2. Integer division. All right. Why is this bad? Yeah, because there are other vector types that also work as vectors. So what I should write is I accept any abstract vector. Here it might be good to have, I don't actually accept numbers, because if I try to do this with a number, that will not work. All right. But any vector is fine. I accept any vector. So this would work on the GPU. It will throw a warning because you do scalar indexing, but it will work. This will not work on with a GPU vector because that's a different kind of vector. All right. Another anti-pattern is to write functions that it's a scalar valued function, but you write the version of the function that operates on a vector. So, for instance, in MATLAB, you can write the sign of a v, where a v is a vector. But the sign is not defined for vectors in mathematics. It's defined for scalars, and it's defined for square matrices and so on. So in Julia, we just write a sign to operate on a scalar, and then if we want to call it on a vector, we just add the dot. And you never need to implement the dot method. They are for free based on the language. So you can always apply any function element-wise. And that's why we never implement the sign of a vector. We only implement sign of a scalar. Another anti-pattern is, I say, rolling your own types. If there is a type somewhere in the ecosystem that does what you want, in Python, in C, in many other languages, it's sufficiently inconvenient to use someone else's code that we often copy-paste their code into our code, and then we modify it a bit, and now we have a new version of that code. In Julia, very often you can make your code work using someone else's types. So it's incredibly common to use existing types for your purposes. And one reason it works so well is that you can extend the behavior outside of the package. So if I if I load the color package that has an RGB type, if that doesn't do exactly what I want in a particular situation, I can extend the behavior outside of colors. I don't need to modify the source code of colors. Okay. The great promise of object-oriented programming is that you should be able to do things like that. But for multiple different reasons in practice, it almost never works. But in Julia, we often don't copy-paste code and change it. We can make use of packages. So try to keep that in mind. See if you can make it work. Very often you can. All right. Condition and return X. What does that mean? All right. The reason I include this is because this is very idiomatic Julia code. You see it used quite a lot. And it's the Boolean short-circuiting AND operator. And what does that mean? Short-circuiting means if this is false, the AND will be false. Then there is no reason to evaluate this side. So if this evaluates to false, nothing will happen. If it evaluates to true, you will return X. So this is the same as if condition return X. But this is a one-liner, and this is used quite a lot, and you can do it with or also. We can read it as if condition and return X. We can also write, if we want the opposite behavior, then we would have cond or return X. Then if this is true, we don't need to evaluate this thing because we know the or would be true. Then we will continue. If this is false, we need to evaluate that side to know what the value of the Boolean operator is. Then this will be evaluated and we will return. It's used a lot in Julia, so it's nice to have seen it and know what it means. So this is perhaps even easier to read in English. Condition or return X. If this doesn't hold, return X. Right? It looks confusing in the beginning. I use it all the time. Other people use it all the time. It's very good. Yeah, I listed a bunch of packages that implements types that are commonly used. So there is a color package. There is a package called distances. So if you write code that reasons about computes the Euclidean distances, the Manhattan distances, whatever distances, if you want to add a new, you have new fancy package that computes optimal transport distance, then you can extend the distance type. And then every code that uses distances.jl will now also work with your fancy distance. That's quite common to use. There are recipes based for implementing plot recipes. So for instance, in control system, we have recipes for a body plot. And we can implement that without depending on the plot package. So when you do load control systems, we don't load the plot package. But if you call body plot, it still does the right thing and interacts with the plotting package in the right way. And that's because there are special types in this recipe space package. All right. And that was it for the patterns and anti-patterns. The next step is, it failed. My discrete PID test failed. And why is that? It's because locally, so this is very good actually. Locally, I have a development version of control systems, or I have the latest version, say. And then something has changed here. There is it says closest candidate is something in deprecated. There is an unsupported keyword argument time. So I might believe when I run the code locally that stuff works, but when I push the change, it will break for someone who just uses the released versions. So now I got that. It says, one test passed, one error. Took 20 seconds to run the test. So now I got here black and white that whatever I did was bad. But we see that the code that was on the GitHub repository, that works. So I have changed something that makes this no longer work. All right, perfect. Yes, the next step is to show you a little thing. I don't know if you can see this all the way down there. Let's see. See if I can make it bigger. Yep. What do I do here? I time something. I time using plots, plot a random vector and display it. You see, it takes a long time. And you have probably noticed this before. That when you start Julia, it took 13 seconds to do this. And that sucks. It sucks for you, it sucks for me, it sucks for everybody. We are well aware of it. How can we improve upon that? We don't want to wait 13.5 seconds to plot something. Right. So what I will do now, we see I call Julia -j with some path to something ending in .so, right? And I will explain later what this thing is. If I now run the same thing, I got the plot immediately. The thing I loaded here, sys 1.8.1.so, is called a system image. So when you install Julia, there is a default system image. So when you call sum on an array, that's very fast because that's built into the system image. Everything in base Julia is built into the system image. But if I start loading a bunch of packages like plots, I run some code, plot some stuff, that is not in the system image. So Julia will compile that the first time. And that is what is taking so long time. This 13 seconds is Julia compiling the plotting package and stuff like that. But now here, when I had called that, the plotting package is loaded, it's in memory, the code is compiled. I can freeze that situation into something called a system image. And that is what I loaded here. Here, when I froze this system image, I had loaded the plot package, I had plotted some different things, and then I said, save this state, essentially. And then when I started Julia, I said, now start with this state I have already saved. So next time when I call that here now, it's very fast. All right. This is very useful.
Question.
Yeah.
Are they dynamic in the sense that you can add to them or remove from them? So say that.
You can compile incremental system images, adding to system images. Yeah, you can. So this is using a package called the package compiler. Let's see here. I think I had a. Let's stop the debugger. Don't save. System image. Yeah. So there is a markdown file in today's GitHub repository that did the benchmarking I just did. There is a link to package compiler, and it gives the following advice. So the benefit of using a system image is, of course, that it's much faster to load the packages that are built into the system image, and it's faster to produce the first results. But there are drawbacks. If you have built in a package in the system image, you can now not update that package without rebuilding the system image. And it takes a couple of minutes to build the system image. Like with plots, stuff like that, maybe 3 minutes. And if you have a package that you are developing, say that you are developing control systems, and that takes a long time to load, you don't want to build that into the system image because you intend to change the code, and then you don't want to use the frozen code from before. But what you do then is that typically the reason a package takes a long time to load is not because the package has a ton of code in it. It's because it uses other packages that also take a long time, right? So you can build those packages into the system image. So in the case of control systems, most of the reason it takes a long time to load is because we use ordinary DFQ. That takes a long time to load. So if you build that into the system image and start Julia with that system image, using the control system package is very fast after that. So I can show you how I have a little script for compiling a system image. What do I do here? I import GR, that's a plotting package. I import plots. I run some plot commands. And this is important because if I just do using plots, okay, loading plots would be fast, but it will still take a long time to actually call the plot. So here I actually call the plot and I call display so that the display code will be compiled and run. I import another plotting package. I use this sometimes. I load static arrays because I use them very often. I do some operations on static arrays. I load Optame optimization package, forward diff. I use that all the time. That space, reverse diff, and so on. Reverse diff I load not because I use this often, but because it's in the trees of dependencies of packages I often use. And it takes 2 seconds to load this package. So I build it in there so I don't have to pay those 2 seconds every time. I use here matrix equations. I called Lyapunov here because that takes a ton of time to compile that. So now I don't need to pay that time. Yeah, and so on. And then in the end, I call package compiler. I list all the packages that I want to build into the system image. And then, yeah, this is all written in the documentation for package compiler. But this is just to show an example of all the stuff I include in my system image. And then I have a little string here so that I include the version of Julia in the name of the system image because the system image is tied to a particular version of Julia. So that's why when I call this system image, I wrote, this is the path, home, this, and the version of Julia.so. And then I said startup file no, because I have a bunch of stuff in my startup file that I didn't want to include. But make use of this if you experience that stuff takes a long time to load. It's quite easy to set up, and then it should be very fast after that. It's well.
Then uses this for half a year or something like that. You will not follow the update. So when you develop control system, you will be starting from half year and version.
So let's see here.
Now and then you must update this.
Yeah. If I in the package manager here it says package status, and then we scroll down, we see here is a line, an arrow with a block. This is blocked from being updated, and that's because GR, I included that in my system image. So if you try a package update here, I can do that. It will probably take some time here, right? But we can see what happens. All right, it said packages marked with this have new versions available but cannot be upgraded. To see why status -- outdated. Then you get, and then it will say cannot be updated package in system image. So yeah, you are blocked from new updates. But you can at any time start Julia without the system image, and you can at any time recompile it. Yep.
Is there some support to do this kind of stuff overnight to say that you can rebuild your system images when you're using the computer?
There is some automatic support in VS Code to build a system image for a project you have. I've never used it, so I can't tell you how it works. There is also a package called automatic system images. Once again, I have not used it. I do it manually.
But you only work with one system image, or do you have a couple of them?
I typically work with one, where I put stuff I know will always be loaded. But it happens quite often that I need to start Julia without it because I needed some new version quickly or whatever. Yeah. So, but if you find yourself, if you work on one project and every time you start Julia to work on that project, it takes 13 seconds to load plots, build plots into the system image. It saves you a ton of time. All right.
Can you add your system image as an example, like on GitHub?
Yeah, I can also link the documentation for control systems has a script to build the control systems into the system image. All right.
One question.
Yep.
If you use like a notebook.
Yep.
Like you can, is there a nice way to use a system image there as well?
There is. I can't tell you how it's done. I never used Jupyter Notebook, but I know you can do it. I think you need to somehow load Julia with a system image and then build iJulia. And that produces a new Julia kernel with the system image or something like that. Don't take my word for it, but I know it's possible. Okay. So now my plan is to go through the homework for next week And after that, those who are interested will go through the homework for this week. We'll go through the slow implementation and some fast implementations, and we'll list the winner of the competition. Where's all right. The homework for next week is very simple. You should create a package with all the bells and whistles of a good package. Preferably, you would make a package for some code you really care about, maybe your research project. If you have nothing you care about, you can package the tracking float implementation from the second homework. There are some requirements. You should include some export statements of names you want to be available outside the package. You should have some meaningful tests, and you should have a decent test coverage. You should host it on a platform of your choice. It could be GitHub or GitLab. It should have working continuous integration, and that's to force you to go through this at least once, because it's so incredibly useful for you with your research project and for you in the future if you're going to work with code that I really want you to go through it. Try to follow the Julia style guide. Have some meaningful README. You don't need to write a ton of text, but just write whatever the package does. And it should be possible to add the package using the Julia package manager, using add and the URL to the package. And if the Julia package manager complains, or if after it has been added, the tests don't run, it's not done yet. All right. You can make use of package PKG templates to set up the folder. You can also just look at the simple package that is already out there. So I showed the discrete PIDs package as an example. It's very simple. It's a single file of code, and it's a single file of tests. So you can look at something like that. All right, that's the next week's homework. And now we're going to go to looking at the implementation of the particle filter. So many of you have sent in implementations, and you have done a good job overall. The results vary several orders of magnitude, and maybe we should start with a winner, actually. Where do I have? All right. The winner by a very comfortable margin is Pix, who was at least one order of magnitude faster than the second fastest. So that is very good. Pix solution, single-threaded, 3.4 seconds, less than a megabyte of allocations, multi-threaded, 374 milliseconds. So that is very impressive. I was initially slower on multi-threaded, so I had to continue optimizing a bit. So I got down to 344, but with significantly more allocations. But that is cheating, so my original time stands at 1 second or something. Then we have varying results. Ylva did a very good job here, single-threaded, 3.7 seconds. I think you were second fastest. And then we have a couple of people on 10 seconds. Actually here, someone multi-threaded, Jonas, multi-threaded 4.4 seconds. This was almost single-threaded, but it used a threaded turbo. So it's, yeah. But overall, good results. And we see that the number of allocations here vary widely. Sorry?
Milliseconds.
Oh, yeah, sorry. Yeah, actually, your max was second fastest multi-threaded. That's also a very impressive number. You have a lot of allocations, which probably makes this a bit slower than it had to be.
Try to remove them.
Yeah. And then we see that some people have over 30 gigabytes of allocations. So we will go through now briefly some code. And I will point out all the terrible things I have done in this code. I wish I had a yeah. All right. The very second line. We see that here I slice along the columns. That's poor memory access because Julia stores memory along the rows like that. Or one column is contiguous in memory. So we should probably permute the memory layout of XP here. Then we allocate a huge array here. We multiply by this, that allocates another array. We multiply by 2, that allocates a lot of arrays. So here are 3 allocations in this particular line. All of them are completely unnecessary. Here we say that W is a log. So here we allocate a bunch of 1s. We multiply, once again allocate, then we allocate for this, and we save that. So here, tons of allocations, all of them unnecessary. So how do we get rid of them? We need to allocate W outside. We allocate W once, and we pass it into this function, and then we keep reusing that memory over and over again, and instead of allocating U here. Here, once again, the memory layout is transposed. We should access the memory as : 1. But a lot of people, yeah.
Regarding those things, that was one of the first things I did, and there was barely any difference.
Maybe it's because there were so many other things that were just slower that's hard to measure the difference. Yeah. So in particular, if these are large, so they don't fit in the smallest cache size, you will see a difference from this. But there are likely other things that are worse. Yeah. A lot of you actually notice that it's completely unnecessary to have a whole matrix of weights because we only use the weights for a particular time step. So we can avoid allocating matrices and just have a vector instead and keep reusing that. So that is, of course, much better. Once again, here we allocate a ton of memory on this line. We slice this vector, and then we allocate to compute the X, then we sum over that, and then the rest here is fine. But there is no dot here, so we allocate to produce the result and save that in here. So if we had a dot here, it would be slightly better, but there is no reason to allocate anything here either. Then we get to the loop. Here I have an explicit copy. You should always be, that obviously allocates memory. We call resample, we'll get to that later. Here again, we allocate a random vector. Then when we multiply with a scalar, we allocate again, and then we add. So there are tons of allocations everywhere. The memory access pattern is bad everywhere. Here we could compute this by just using a view. This slice allocates, but if we had said view in front, it would be allocation. Right, and it's the same story everywhere here. We keep on allocating everywhere, and here we compute the element-wise product and sum. We can do that without forming a vector of the element-wise product and so on. All right, resample. This is terrible because here we compute a vector with weights that are exponentiated, then another vector to do the cumulative sum, and then we create yet another vector to concatenate the number 1 here. So here we can just write a single loop. We can see how that looks in my optimized implementation. Here's a single loop that does the cumulative sum in place in something that is already stored. Bins that was allocated outside, passed in, and I just do the loop, and it's no allocations inside here.
Is that the same as CumSum with exclamation mark?
Yes, it is. But I still wanted to have this 0 also. So then CumSum with exclamation mark didn't really work for me. But you could probably make use of that and avoid the allocation. Sure. All right. Then we have, this is a red flag. These are global variables that are not declared constant. Absolutely terrible for performance. Just writing const in front of them solves the problem completely. Then here we have our dynamics and the measurement function. Here, once again, we just allocate a lot of memory. So what I did in my optimized implementation is that I modify X in place here. So this is already a vector, or maybe I even created a, let's see here. Where do I have that? Here's my optimized implementation. It takes X, time, and the number of particles, and there is a reason I pass in the number of particles. I can't call length of X. I will get to that later. Add fast math, I can accept some performance hit in the cosine implementation. Add turbo to make sure this uses simd. Then I have a separate loop to do the random numbers because that the turbo doesn't, the semantics of turbo is such that it doesn't allow random. I split the loop up into two, and that was beneficial. But you see, I always update the existing memory. I never create any vectors. These are all scalars. XV is a scalar that I got here. And then once again, I just call rand. This is a scalar, and I update that in place. So no allocations in this function. And the same goes for G. And here in G, there is a multiply by den, because originally I divided by a sigma. A division is an expensive operation. So division, it's very fast. It's a nanosecond or something. But compared to the other arithmetic operations, a division is more expensive. So I can pre-compute the division, and then I just multiply here. That's faster. And of course, it's a constant. And you see also, I have a bunch of float 32. Some things here, F0, that's a float 32. Some things I do in floating point 32 precision instead, because it's sometimes twice as fast. The weights, however, are probably in float 64 for numerical reasons. All right. Let's continue. Here, everything here in this loop is in global scope. Absolutely terrible. This should be in a function. Then there are a bunch of loops, 4, 4, 4. All of the loop iterations are independent, so I could thread them naively. Indeed, that does work very nicely. What do we see here? There is not super much here. I allocate a bunch of vectors here. I could allocate those outside and so on. I compute the dynamics forward in time once to stimulate the true dynamics. That's no particular problem. But let's now look how this could look in an optimized implementation. I define a struct called a workspace. This contains all the memory that a thread needs to perform the computations. It has X, Y weights. It has a separate weight for exponentiated weights, the bins for the resample, and the particles. You see, some are float 64, some are float 32. Weights cannot be float 32 because then you get too poor numerical performance accuracy. I have a constructor for that. I have put the test in a function, run test. Here I hard code 12 workspaces. I create that using special syntax because I have 12 threads, and that I do that, so we know we have exactly 12 workspaces. I have flipped the order of these vectors. So it starts with the largest one and ends with the smallest. And why do I do that? The single most expensive simulation will be when you use 10,000 particles and 2,000 time steps. I want to make sure that that simulation starts immediately. Because if I start that simulation last, then all the other threads, they will compute, and then we will wait for the single thread that does the expensive simulation. So I start with the most expensive first. Then I allocate some stuff outside the loop. Then the modification I bit from my currently most optimized version, and the one I said took about the second thread, is because a few years ago in Julia, if you had a thread on a loop that used a static thread schedule, and it didn't compose with inner nested threads. So I used threads on a single loop only. But then we would have significant amount of time where some threads were just idle because they were done with their computation and they couldn't start anything new. Currently in Julia 1.8 or possibly 1.7, there is another default scheduler, which is more dynamic. So now I can thread all the loops. And that just creates more tasks for the thread. So as soon as a new thread is available, it can start on a new task. And crucially here, inside the innermost loop, I extract a workspace that belongs to the particular thread that is running. So since I do threaded, I can just pre-allocate memory outside and reuse that. Every thread needs its own memory. And if we look at how I allocated it, I allocated with the largest number of particles and the largest number of time steps. So all threads have memory that fits the largest simulation. And I could perhaps get away with slightly less allocations if I did that smarter, but laziness struck. But crucially here, I get the workspace that belongs to the thread that is running. I unpack all the arrays, and then I create views so that they now have the correct length and so on. The reason I passed in the particle count and the number of time steps is because first I didn't actually bother to make the views, and then I needed that information in the other functions. But when I create the views, I no longer need that information. Here I do things in place, no allocations. I said fast math here to potentially make use of a faster multiply and add. And then I call my particle filter implementation, and I pass in the memory I've already allocated outside. So now all the operations in here, they use the pre-allocated memory. So I allocate 12 times, one for each thread. And then that is reused for all the thousands of the simulations I do. And then I have just naively added the root square to the E here. That is incorrect in a threaded context because there might be a race condition. Laziness. I saw someone actually use atomic add. Was it you? Yeah, nice. That's how you're supposed to do it. Ulla?
Yeah, it was a bit hard to catch everything, but so this XH, XP, etc. Are they static?
No. So
or what did you allocate?
my constructor for a workspace. Here I say in the struct I have a bunch of vectors. And this is a constructor. It takes the number of particles and number of time steps. And then I just create a bunch of allocations, and I store them here. So they are regular Julia vectors. But I only allocate them once. Here I create 12 workspaces. And then inside the loops, I never allocate anything else. So when I come to a loop, 3-threaded loops, and inside here I just say, get me the workspace that belongs to the current thread, thread ID. And thread ID is a number, in my case here, between 1 and 12. So that gives me that particular memory, and there is no other thread using that memory. So I'm free to use it in this thread. And then I just make use of that and pass it into the particle filter. Yeah, and then I... Yep.
You're using a left.
Yeah, that is, okay, I can tell you because you asked. There is something called the slow closure bug in Julia. So if you create a closure over a variable that has been assigned outside here in the function, that variable will be boxed inside the closure, which means that the compiler doesn't know the type. So that will cause some additional allocations if I don't do that. If I write this let, and I just say n is n, now n is frozen in time to whatever it happened to be when I enter the let block. That is sufficient for the compiler to optimize away the boxing. All right, but if that doesn't make sense to you, don't bother with it. It appears occasionally. It's good to be aware of if you want to write super high performance code. So I did it just. Yeah. Exactly. The thread macro creates a closure for the loop body. Yeah. So that's why that problem appears. But yeah, that is an unfortunate situation based on the current. So the compiler is divided up into a parser and the other compiler steps. And the mistake here is that the parser doesn't know everything it needs to know when it parses the code. And yeah, I don't know. I can't give you more detailed information. But it appears if you do a code warn type on this, you will get a bunch of red printouts saying compiler core.boxed. on for instance, on the workspace vector here. That's an indication that the compiler doesn't know what type workspace is. But if I do this trick, then suddenly it knows it. Yeah. All right. So from, I don't remember the timing on the original code. I think it was 80 seconds on my machine at home. And you can push it down to 350 milliseconds. And I think we could reduce the number of allocations. PEX reduced it way further than me, the number of allocations. It's my initial attempt was 26,000 times. And with PEX, it's probably yet another 1,000 times or something. So the difference between this is perfectly, the old implementation is perfectly valid Julia code. And this is perhaps how you would write it in MATLAB or Python. But in Julia, we have the option to write much more optimal code. And we need to think about stuff like memory layout. We need to think about things like what causes allocations. Do I need to slice the vector? Can I use the view? Have I missed any dots? If I don't have dots here, then I will allocate for each view when I multiply a scalar by a vector. That causes an allocation. It's a lot now, but for me, who has written Julia for a long time, and I often think about those things. They are obvious, and they in my ryggmärgen, in the spleen. Yeah. So it's not that hard once you get used to it, but you need to sit and mess with stuff like this for a while to get it into memory. Okay, since PEX won, there will be a prize at the last lecture. But everyone else also has done a decent job. Some people have yet to send their implementations, and yeah, I will come with detailed personal feedback during the week. A lot of people sent their submission last night, so I didn't have time to send. All right. Yep.
Did you send out your solution?
I think you do.
Yeah, if please don't post it online though, because I reuse this thing each year. I give this lecture.
You can send it.
I can mail it. I can mail the solutions, but please don't post them anymore. So I don't have to invent a new exercise.
Very good.
Thanks. Yeah, it's a very low-level numerical code, the kind of code you might implement as a control person. You do simulations, and it's also numerically intensive code. If you write it bad, it might not be feasible to run such an experiment. But if you write it well and it's 1,000 times faster, then yeah, it's suddenly feasible. It enables new kind of research if you can do things fast enough to be relevant. And this particle filtering, stuff like this, where you do the same thing in parallel multiple times, you can use a cluster to run it in parallel on. We use 12 cores for this benchmark on my machine at home. You can easily use 128 cores on Cloud One or something like that. Right? That's very easy to accomplish also. All right, cool.